Hello again. Now we are going to continue to learn the simple modeling techniques we are going to see in the following parts of this course when we are trying to create mathematical models for realistic problems. In the next presentation file, we are going to classify these simple modeling techniques under 4 items. First, we are going to see how we can play around model to obtain a standard form of mathematical model. This standard form is always useful in running the simplex algorithm for linear programming type of mathematical models. However, we can also practice these tricks on different kinds of mathematical models in order to simplify them. And in the third part of this, we are going to see how we can create an unconstrained mathematical model by removing the constraints and write them or introduce them as a penalty function in the objective function. There are many ways of doing that, and there are some important practices which help us to gather information about the objective value of very complex problems. So while you are removing the constraints into and add them into an objective function as the penalty function, you are basically creating soft constraints. You are not stating that all constraints must be satisfied. However, again, by the solution of this soft problem, you can identify a boundary for the optimal objective value of the original problem. So we are going to see about that. And in the second part, we are going to see how we can create dependence between constraints. So there are many situations where we have to satisfy a subset of a sequence of constraints. Okay, so far in the mathematical models that we have seen, we have stated that the constraints, they are creating a feasible solution space when they are intersected. So when we give a list of constraints in a mathematical model, we always state that the feasible solution must satisfy all of them. Therefore, it resides in the intersection of the solution sets of these constraints. However, such a situation may not occur at all times. There may be some cases where we need to satisfy at least some of a sequence of constraints. We do not have to satisfy all of them. So such a complex situation can be modeled again by using spatial tricks and binary decision variables. We are going to see about those. And we are also going to cover a topic which we have covered earlier with a small instance. This time we are going to consider all typical aspects of this situation. When we have a constraint which is defined in absolute value, how we can replace these constraints with constraints which do not contain any absolute value in it. So if the contents of the absolute value function is linear, then basically this is going to be called the linearization of the absolute value constraints. Now we have already seen about an example, seen about this in an example, and we have stated in that example we have seen that the absolute value of a linear function was supposed to be less than or equal to some right-hand side. However, in general, these absolute value constraints are not forced to be less than or equal to form. They can be either in greater than or equal to form, or sometimes the absolute value of a function of decision variables must exactly be equal to a certain right-hand side value. So in that case, there may be multiple constraints that we need to introduce just for removing the absolute value constraint. In the third part of this presentation file, we are going to see how we can use the binary decision variables for other purposes. We can introduce yes or no decision basically with a binary decision variable. We have already seen about the knapsack problem. If you remember, in the 0-1 knapsack problem, the decision variables were representing a decision which indicates if we are going to take the goods in our bag or not. And we are basically trying to do that for all possible types of goods. So here, the binary decision variables were indicating a yes or no decision, which is indicating whether to take or not to take the goods. Now, there are many headers here, again, which are going to be using binary decision variables to simplify things. But at this point, it's very important to explain all of them one by one. So we will see what kind of applications we can do or simplify by the use of the binary decision variables. And even though you will not be able to understand these applications at this point, let me tell you that these applications, especially, which are going to be mentioned in the third section of this presentation file, are going to be used very frequently in the future parts of our course. Finally, we are going to see how we can linearize some nonlinear models. There are some practices, examples, some problems in which we are going to end up with a nonlinear objective function or nonlinear constraint. We are going to see how we can linearize some of these nonlinear models in application. We are going to see the concept of fractional programming, again, which will be linearized by the change of variables. All of them are going to be analyzed under the final section of this presentation file. Now, let's move forward a little. What we are mentioning about playing around with the model. Now, you see, there are many ways to define a mathematical model. For example, instead of writing an equation or inequality in the way that we have seen in the model, we can simply multiply it with -1 and swap the inequality sign, and we can achieve different kinds of forms of the same mathematical model, each of which is going to end up with the same optimal solution and the optimal objective value. Okay, so we are going to see each of this. In the first part, we are going to see how we can remove the unrestricted variables. Now, through the applications that we have solved so far from the first week, we have not seen such a case, but there may be some decision variables in mathematical programming models which are not restricted. So in all applications so far, we have seen that all decision variables were to be non-negative, which means they are either 0 or equal to a positive value. Now, there may be some practical situations, and actually which are very frequently observed. The variables may be unrestricted. For example, if a temperature value is a decision variable for us in a mathematical model, we know that the temperature can also take negative values as well. So 0 value is simply the temperature that freezes water, right? So we know that, but 0 is not basically a natural origin point. So basically, the temperature itself can be a decision variable which can take negative values as well. So depending on the unit that you are using for temperature, of course. And also the money, for example, profit, can also take negative values as well. Because when profit is positive, we know that this is actually a profit. But if profit takes a negative value, then it means a loss. So if we say that in the end of the day, the profit is -$5, this means you are actually losing $5. Therefore, in some cases, when we are introducing such a variable into our model, we should allow that it can for to take a negative value as well. So these variables are also called free variables in our models. And how are we going to deal with this situation? Because we know that if you have a linear programming problem and all of the non-negative, all of the decision variables are non-negative, while one of them is free or unrestricted, in that case, we will not be able to solve that problem using the simplex algorithm, because simplex algorithm requires all decision variables to be non-negative. So how are we going to deal with the situation? You see, we have a mathematical model where the objective function is the minimization of a linear function of 4 decision variables, and we have 2 inequality constraints in the form of a greater than or equal to inequality, and we have x1, x2, and x3 used as decision variables in the first constraint, and x1, x2, and x4 are used in the second constraint. And we are forcing the first 3 decision variables to be non-negative, while the fourth decision variable is unrestricted. Now, what we can do is basically this. Maybe most of you have already known about this through the operations research course. We can say that x4 as a free decision variable is equal to the difference of 2 non-negative decision variables. So x4 is going to be equal to x4 prime minus x4 double prime. So both of these decision variables are going to be non-negative in the end. However, because we are not putting any restriction between these two variables, whichever is going to be larger from the other one, it is free to choose. Therefore, in the end, the difference here can either be negative or positive or 0. And we are simply replacing every x4 that we see in this model with x4 prime minus x4 double prime. So we are basically representing an unrestricted variable as the difference of 2 non-negative decision variables, and we are not putting any constraint between these two decision variables, whether x4 prime is going to be large or x4 double prime is going to be large. It is going to be decided by the objective value. In order to minimize that, the assignments will be made. However, every constraint that contains x4 in it will be satisfied again when you replace all x4 values as the difference of these two non-negative values. Now, in the second model, you have a mathematical model with 5 decision variables, and again, 2 constraints, and these 5 decision variables, all of them should be non-negative. Now, another type of trick that we can apply is to change the constraint type and the objective type in mathematical models. We can convert inequality constraints into equations or equality constraints, or we can convert an equality constraint into inequality constraints, multiple inequality constraints actually, and we can change the maximization objective function to a minimization objective function, or vice versa. So how we are going to do this are explained in this page. Now, let's just say you have a constraint in the inequality form, and the left-hand side is a linear function of decision variables. Actually, such a trick can also be applied for other type of inequalities, not limited to the linear functions or linear type of constraints. However, we basically have seen the practice of this in the operations research class for linear constraints already. So let's practice it again. If you have an inequality in the form of a linear function on the left-hand side of the decision variables, and on the right-hand side, we have the upper bound of the activity level, total activity level as B, how you can convert this inequality into an equation type of constraint? Basically, we know that by assigned values of x1 to xn, this constraint will either be satisfied in the equation form or in the less than inequality form. So this means we will either observe a 0 difference between the right-hand side or left-hand side, or a positive difference when you subtract the total activity level from the right-hand side. So this means the slack between the right-hand side and the left-hand side will either be 0 or positive. Therefore, we say that Additional to the activity levels, we are adding a slack variable, which is the complementary activity level that exactly makes the total activity level equal to B. Now, this slack value should be greater than or equal to 0. Otherwise, if S is negative, then this means the left-hand side of the original inequality constraint can exceed the right-hand side. Therefore, we are basically adding a slack variable in the end of the left-hand side as addition, and it is supposed to be non-negative, a non-negative slack variable, and this constraint will be written in the form of equality. A similar situation can be written for the greater than or equal to constraints. So this time we know that when you subtract the right-hand side from the left-hand side, obviously you are either going to get a 0 value if this constraint is satisfied in the equation form, or you are going to see a positive value as the difference. So a1 x1 plus blah 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 plus an xn minus s should be equal to b, we say, and s should be greater than or equal to 0 in that case. Now, this s is called the surplus variable here because we have a resource, an activity, total activity level on the left-hand side, which should exceed the right-hand side. So there is a minimal amount of activity that we need to perform. However, if you perform the total activity level more than this minimum level, so you are adding a surplus activity here on the left-hand side. Therefore, we say that when you subtract the surplus activity, you need to get exactly equal to the minimal activity level on the right-hand side. So S is again going to be greater than or equal to 0, and this inequality constraint will be converted into an equation form of constraint. Now, we have seen how an inequality is transformed into an equality constraint. What you can do for an equality constraint to convert it into an inequality constraint is to write it as two inequality constraints. Now, indicating that the left-hand side here to be exactly equal to right-hand side, this means the total activity on the left-hand side is supposed to be both less than or equal to and greater than or equal to the activity level B. Because in the intersection of these two inequality constraints, there is only a feasible situation where the total activity level is supposed to be exactly equal to B. So you remove the equality type of constraint here by introducing the same left-hand side and the right-hand side, again, in two inequalities. The first of which is going to be a less than or equal to inequality, and the other one is going to be a greater than or equal to constraint. Again, if you want to see a greater than or equal to form of inequality instead of a less than or equal to constraint in your mathematical model, you can simply multiply both sides of the inequality with -1 and swap the inequality sign in between. So the sum of these activity levels to be less than or equal to B, it also means that the sum of the negative activity levels to be greater than or equal to -B. Again, you can do vice versa if you have a greater than or equal to sign, and if you want to swap it with a less than or equal to sign, again, you can multiply both sides of the inequality with -1. Again, you do not have to forget, you should not forget to swap the sign in the inequality to the other way. Then finally, we can change the objective type. If you have a maximization problem where the objective value is equal to sum of activity levels or sum of cost components, let's just say. Here in this example, we see a linear function of the decision variables. Again, we are not forced to have a situation like that in order to use this trick. We can always change between the maximization and minimization type of objective function, whether the objective function is linear or non-linear, it doesn't matter. However, the trick is what? The maximization of this objective function is actually the same as the minimization of the negative of this objective function. So when you define z as the sum of these values, and y is going to be equal to minus z, which is the sum of these activity levels or costs, again multiplied with -1, maximization of z will exactly be equivalent to the minimization of y in that case. Basically, multiplying the objective function with -1 to swap between the maximization and minimization. Again, a minimization type of objective function can be converted into a maximization type of objective function, again by multiplying the objective function with -1.